Where are we at?
We're at the Science and Technology Facility Council.
Yep.
RE9 Data Centre, the home of JASMIN.
So I thought I'd do something a little bit weird today and show you this is actually a data centre where I've been privileged to work on and off for, I don't know, 6 or 7 years, I guess.
Yeah, something like that.
Yep. And we've actually been building this really strange network that's actually a high-performance compute infrastructure.
Yeah, we call it a super data cluster.
Super data cluster.
Super data cluster, yeah. So it's like half a supercomputer, but more storage than it has to compute. Very unusual. Yeah.
Okay, so we're going to go around a little bit and let's see how that looks. This is one of my favorite things about this data center, is that you've actually got to walk over these glass tiles, and it's really disturbing when your feet are standing on top of a glass tile.
This is the robot toy. So inside here we have 2 of these storage tech robots. 8000 has 10,000 slots, 10,000 tapes, 8 terabytes to go.
Yep.
Do the calculations, that's about 180 petabytes of storage. Yeah.
So it's a lot of storage, but the fun part about this is that this is still the cheapest storage you can get.
Yep, that's right. So everybody says that tape is dead, but tape, believe me, is not dead.
But this is like 180 petabytes. Now, one of the things that I think you told me years ago is you don't actually use this for backup.
Correct, yeah. Some of it we use for backup, for the critical golden data sets.
Right.
But most of it is just used as what we call elastic tape.
Right.
So in JASMIN terms, so in these robots, it's not all of the data, but we have about 40 petabytes of data in here on about double that number of tapes.
Yep.
And so we use that just to shuffle the data backwards and forwards between tape and disk.
So live and not live, or near line or offline.
Yeah, because even with 45 petabytes of high performance storage that we have on JASMIN, you can't use all the 45 petabytes at one go. It's just impossible. Right. So you have to work through it, and some of it just stays offline.
Now, the other reason that they don't use it for backup is because if something went wrong and you had to restore it, it would take weeks.
Oh, yeah, months probably.
Months probably.
Yeah.
So tape's great for storage, but not so great for backups because not because it's bad for backup, but because it's also a problem to restore in a timely fashion when you're working very large data sets.
So even with our enormous network, we'd be bandwidth bound by the drives here.
Yeah.
But if you think people have done experiments now with moving a petabyte of data a day across the WAN on a 100 gigabit circuit, and if you're really, really good at it, you can get 1 petabyte across 24 hours. Right, 1 petabyte in 24 hours. Well, we've got 40 petabytes on here, so you could do the calculations, right?
It doesn't take long.
No. Yeah. Well, no, it does take a long. Get off here, right?
It doesn't take long to do the calculation.
No,
it's unfeasible. I think was what I was trying to say.
Yeah.
Now, the other thing about this is just how big this unit is. You may not see it from here, but if I try and get back far enough, I'll walk you around, but it's enormous, right? It really goes back a very long way, and you don't realise just how big those tape robots are because they just take up so much.
But if you're trying to do 180 petabytes on disk, right, that's going to take up a lot more space than this does, and a lot more power as well.
That's a good segue because we'll go and look at the storage array, which is 45 petabytes.
That's right, yep.
Okay, so where are we now? Now, I think we've just looked into the networking because I recognise some of this as familiar.
Sure. So this is the heart of what we call the JASMIN Phase 4 network. So for JASMIN, JASMIN's been in 5 phases, 5th phase is this year. But for this phase, we had to build a brand new leaf spine design. And it was fairly clear that when we did that, we were going to have to bolt what is already a huge 12 spine leaf spine cloth tree. We're going to have to build a brand new one of those at 100 gigabit. So that's what we're seeing here.
So the J3 network, which I helped you design, was two tier. It had 12 switches in the spine and 30-something switches in the leaves.
So it's about 28, we could have gone to 36, but we had 28 leaf switches.
And how many servers did you end up with in that?
There's about 350 servers. In total, there's about 1,200 machines on that side of the infrastructure, both physical and virtual.
Right.
Yeah.
So it sort of adds up over time.
Yeah. Right.
Now this time we actually scaled up to a lot higher. We're talking something like ready to build out to about 3,000 to...
Well, so this time we're going for larger numbers of servers. So we've just, we haven't filled this infrastructure up yet, which you'll see from the pictures, but we've got about 220 servers. These are all 2 by 25 gig equipped servers, so we can do a lot more of those than we could with the 10 gigabit infrastructure on the JASMIN 2 side. Yeah,
and now the really cool thing about this is because it's 25 gig, 50 gig, 100 gig.
Yeah.
You've got some servers at 25, some servers at 50, and some at 100, but all the spines are at 100, ready to go to 200 and 400 gig.
Yeah, that's the plan. So we have an infrastructure in this machine room, which is we've linked together at multi-100 gigabit. So probably about 2 to 3 terabits per second across the Superspine.
Yeah.
But we have another data center across the road that we need to patch in at that rate, so it's non-blocking.
Yeah.
So we're not squeezing it through a pipe. We need to make that data center appear as if it was here.
And that was a really interesting design challenge because the data center is physically on one site, but split across 2 zones because you've run out of space in this facility.
Yeah, that's right. Yeah. So we're going to need to do that. We have a demand for about 300 petabytes on hopefully on disk in the next few years. We're only at 45 right now, but it's fairly clear that although we could squeeze 300 petabytes into this kind of space, it's going to be a tight squeeze. Maybe with those 70 terabyte drives we were talking about earlier, maybe it'll be okay, but who knows?
Yeah, I was at a session last week. You might see a video coming out, but Seagate's talking about 30 terabyte drives in the next year or two, and they think they're going public with getting to 70 terabytes by 2020 in a single drive.
Either way, it's quite likely that given all the other infrastructure that's in here as well, not just JASMIN, that we are going to need that space, and we're going to have to stitch it in at those extraordinary data rates.
So for those of you watching, what's actually happened, you might have seen as we walk down the aisles, you'll notice that this the networking rack is in the middle of the aisles, and that's because all of the storage arrays sit in these 2 aisles. So this is actually at the central point, so the cable radial's out. And that's really important because the SFPs are actually the most expensive part of this network.
Yeah.
The switches themselves are, relatively cheap compared to how much it costs to get the 100 gig, 25 gig, 50 gig, and because you have to get them for both sides, because the 25 gig needs to be in the server as well. And so it's those cables which really cost money. If you're coming from a 1 gig environment, you may not know that.
We did an analysis with very early on in the first phases of JASMIN where we were looking at just the cabling cost alone, and we worked out that the fibre was cheap, but the widgets on each end of the fibre were going to cost us about 100, or in those days maybe £200 a go. So for each cable was going to be we needed hundreds and hundreds of them. And the actual cost of the network, the physical cabling alone was just going to be extraordinary. So everything we've done in JASMIN is all direct to tap AOC cables. Yeah.
Using the active op, and that was actually one of the key decisions in the early phases, wasn't to get focused on the switches, but to get focused on the cabling pricing, because a design that could reduce the cabling could reduce, and even the Superspine architecture that we've got here is a butterfly design because it reduces the cabling cost by about 40%.
Yeah, it was a massive deal.
Yeah.
And when you try and look at the cloth tree network, when you actually look at a picture of it, you go, oh my god, this is far too complicated, right? Cables going everywhere. But when you actually think this is the spine rack, we've got 8 switches here, and the leads are just scattered in the adjacent racks. It's actually, all you're doing is just cabling back to a rack. It's actually, the infrastructure's not that hard to construct, even though it looks really complicated.
Let's go on to the next section, stay with it. So this is the Superspine. So this is actually the 3rd tier of the Clos architecture.
So this is now the heart of the data center network. So we built this originally for JASMIN to connect 2 pods together. So the 2 Clos spines that we've just talked about. But we also wanted to be able to stitch in all of our other infrastructures as well. So we have a similar infrastructure for the processing we do at CERN, so the CERN Tier 1, similar size to JASMIN, and sometimes we need to communicate between those 2. We have other infrastructures in the data center as well that we need to patch in. And once we've gone to 2 pods in JASMIN, it was suddenly become obvious that those other infrastructures were just other pods. And if we did the correct thing with the Superspine, we'd be able to patch those in. So the reason why the Superspine doesn't look particularly populated right now is because that's for future expansion and also to connect those infrastructures in.
So the real key to this part, this Superspine, this is actually 12 switches that are all nominally 400 gig ready. And although we're just using a few, the cheer here is that there's many different departments inside of this organisation, and they're all talking about migrating onto this spine, so there's one network in between them all. It actually took quite a bit of work to get this architecture together, because getting all the departments to agree was really quite an interesting process. But that's why it's half empty, is because we've got another few thousand potentially systems that are going to hook in, and it's going to be Clos 5-tier architecture or 3-stage architecture. And this will just, and that extra capacity is there, so these other departments can join in and connect at terabit speed. Quite unusual design. This behind us is the storage aisle. It's very boring, it's a little bit windy, so I hope the microphone can pick it up. But this is like, what, 45 petabytes of storage?
Yeah, so this is about half the storage in here, or half the physical service of the storage, but most of the capacity is in here. So about half of these two racks that you're actually looking at, that's about 45 petabytes raw, about 35 petabytes usable, something like that.
Now, the interesting thing about this storage is it's not a storage array, it's just servers with hard drives in it. So it's actually an IP storage made out of JBoss.
Yeah, so it's software-defined storage. Well, the later part of it's software-defined storage. We just moved into that this year. So previously we were using appliances, and that's done us very well. But it's not produced the cost per terabyte we want at the performance and with all the features. So we're kind of moving on.
But when you're buying 45 petabytes, cost per terabyte really matters. It's not like it's a storage array that needs, special loving care and chassis and power supplies and all that sort of stuff. It's just about, I need a lot of hard disk drives. And the question is, how do I get that many in a single space? So as you can see, it looks much more heroic on the camera, I think, than you really think. But that whole aisle, that has actually the cold aisle down there. What you can see is this has a row above it, and all of these, in between every 4 or 5 racks is actually a chiller. So not only is the whole room actually chilled, in this particular aisle there's chillers in here alone, because there's so many disks and so many servers that you can't actually produce the cooling that you need. And so there's all of these APC chiller units in between every 3 or 4 or 5 racks to keep the whole aisle. And you can't see it here, but up here, these are temperature sensors. And those temperature sensors go all the way down because you can have hotspots down the trail, and they actually monitor each of the temperature sensors. One of the stories that you told me, if I remember rightly, was the time that you actually found that the Mellanox switches were overheating, and that's because they were too close to the floor. They were actually blocking the extraction.
Yeah, you can get into that trouble. Yeah.
And the only way you found that out was because you had temperature sensors every 10 inches down the rack. Anyway, we'll have a look at one more thing, and then we'll wrap up this tour. So what are we looking at here?
So this is the back of one of the 25 gig equipped racks.
Right.
So the key thing about this is, and the rest of JASMIN, that we're doing non-blocking networking throughout.
Right.
So here we have 2 by 25 gig, but the uplinks from this rack give us enough bandwidth to support that without any blocking at all.
Yeah.
And that's one of the keys to JASMIN. We're talking about a storage system which is multi-100 gigabyte a second. Probably at least in the top 10 in the world for I/O performance, maybe in the top 5. We don't quite know at the minute. We're still trying to make. We've benchmarked individual bits that are maybe 140 to 250 gigabytes a second. If you put all the bits together, it's about 500. But the benchmark for actually measuring it, IO 500, is actually quite an interesting benchmark to get working on an infrastructure like JASMIN. We're working on it, and we'll get there eventually. So.
And we often talk about how a lot of the other high-performance compute networks are all using InfiniBand, and you're one of the few in the world, perhaps the only, that are actually running Ethernet for the storage cluster.
Yeah, so we're doing this all without, just on Ethernet alone, no InfiniBand. Well, that was a conscious choice. When we looked at doing InfiniBand, it was quite it was an additional thing that my team would have to manage. Yeah. So you'd have islands of InfiniBand, you'd have islands of Ethernet, and when we looked at the low latency Ethernet, we could get within about a factor of 2 of the latency that we needed for MPI and parallel processing. And JASMIN is a data center, a data analysis platform, not a compute engine. So we could actually take that leap, get rid of all the InfiniBand, and just have one network that did everything. And we run everything over it. So we run block storage, we run POSIX network attached storage, as well as all the compute across that. And because it's non-blocking, we don't get into any of the traditional problems. So.
And just for the record, it's really hot here. You've got no idea how much heat these things are thumping out. You can actually break a sweat just standing around these things. It really is uncomfortable. This is the original rack that we put together for the first stage of the network design. It was about 5 years ago, I think. The really cool thing about this rack is they actually put lights in it.
Well, believe it or not, the lighting is actually to help us manage this crap in here. It does help you actually see what's going on, but it's also one of the feature points when we take people on tours. Nowadays, we're actually showing it as a way not to do things, whereas the JASMIN 4 is a little bit. One of the problems with JASMIN is it's kind of grown, I wouldn't say topsy-turvy, but we're now at 70 racks, and we've gone from about 10 racks to 70 racks in 6 years. It's a huge infrastructure, so some of the problems we got into, you don't know until they've actually hit you.
Now, one of the interesting things about this rack is it's always been full from the day we first started. because we fully loaded out the network. We built the network completely and pre-wired all of the switches in from day one, and it really hasn't, it's always looked horrible like this since we started, really.
Yeah.
One of the interesting things about the network that we did 5-6 years ago when we first put that together was there was no network automation, but we were really focused on operations, because you were telling me how you just didn't have any headcount to do stuff. And the trick that we came up with, it took us a long time to do it, was basically every switch had 50 VLANs configured in it with 50 IP subnets, and they're all put into the OSPF. And then, as I understand it, you've never needed to really change the configuration of the switches except to put a port in and out of a VLAN.
Yeah, no, that's right. My team are not specifically a networking team, so there's just myself and 2 others, and all we really want to do is just patch servers between different VLANs. If they're already there, it's very easy for my team to just go to a GUI or whatever, just press go, connect this thing to that VLAN, and not have to worry about all of the routing and the OSPF and now BGP on top that's happening in the background to connect them up together.
Yeah, and that was the other thing we did to keep the network stable and to reduce the operational cost, was no layer 2. So there was a small segment where we built some switches into MLAG, and then we hooked them into the spine. But by removing the layer 2, we took out a lot of the instability. Now that required you to go back to the vendors and change some of the way the storage worked and tell them to use layer IP instead of Ethernet. But they were able to do that because of the size of your installation, and it did work out pretty well in the end, I think.
Yeah, no, it's worked out really well actually. I think when we first did it, it was a big shock. This data center has traditionally just been layer 2 only.
Yeah.
So we had /21 VLANs kind of all over the place, and occasionally, of course, you get into the /21 VLAN problem, which Greg was not very impressed about when he first came here, for good reason.
So this was the network when I first arrived was a little bit of a, it was obvious that people had been working on InfiniBand because there's only L2 networks. And so you just hooked everything into the switches. It was like one big flat L2 network, and there was thousands of hosts on it. But anyway, we won't talk about the bad things. We solved that problem pretty quickly. Finalising the problem actually took about 5 years to unpick all of that, but it's all sorted out now. But getting onto the L3 was actually a key part of reducing the cost of ownership. It wasn't actually about the reliability, although that was part of it, but it was also about just making it easy to operate, because they have no full-time networking people. The only people who would be looking after the network was a sysadmin. So how could I do that? And in the end, I just said, well, let's just put VLANs and IPs everywhere and then waste them. They may never be used, but so what? It'll still solve the problem for 3 years, which I think it did.
And it's really proved its worth now. So all of our data, all the other infrastructures are trying to move to this kind of architecture as well. It just solves the, although it's complicated to set up and get your head around it initially, but it does solve. I mean, basically, we've never had a classic layer 2 issue in the whole 5 years since that was installed now. Whereas before we had, I think 2 or 3 in the first year. Fortunately, it didn't affect the users, but it was really bad.
Do I get to say I told you so?
Yeah, yeah, Greggy told me so. Yeah.
So what is it about this aisle that I should be thinking about?
Okay, well, for the start off, it's quieter. And one of the reasons is for that is because we don't have inline chillers in this row. You probably wouldn't have seen that from the previous picture. But in this row, we have racks of storage and racks of compute. And if you were to look very carefully, you'd note that we have like a rack of storage, which tends to be the hot racks, facing racks of compute. And that means that the airflow that's coming out of the ground here gets shared between the two. We can't have compute and compute opposite one another like we can in the opposite aisle because of that problem. There's only so much cooling. So here we're talking, the rated is about 10 to 12 kilowatts a rack, something like that, based on the airflow in the ground. We can probably get up to about 15 if we do about hand waving. And as I designed this, to actually split the storage and the compute so that we averaged out. And we've been fine with that approach.
And that's an interesting challenge for the network, because the racks are distributed in certain patterns. They're not optimized for the network or for the cabling, they're optimized for the airflow, and that's increasingly a problem. But for high performance compute, or data centers like this, the actual airflow and the cooling and how you put the energy and get the electricity actually can define where the network gets to go and where the cabling gets to go. And it's something that you need to think about as a networking person, that you don't get to define it, or you don't get to make the rules. The rules are made for you by issues you can't control.
No, it's really easy now. You don't have to worry about adjacency between racks. You just pick a rack and just drop some cables in. It's absolutely fine. In JASMIN 4, one of the things we were looking to crack was to avoid this, having all the storage eggs in one basket. So one of the issues that we occasionally got with the previous storage was that you come to do a software upgrade on the storage, and that required taking everything offline. But the problem was that the users couldn't log in because the home directory was on the storage, and that meant everything was out. So in the JASMIN 4, we were trying to look for a piece of storage that could just sit on the side, would not be affected by that 45 petabytes of storage. It only had a few hundred terabytes, and could be quote unquote, solidly resilient, didn't require firmware, or at least firmware could be done on the fly, and would be fast. So we were looking for something that we could do fast compilations on.
This is the only traditional storage in the place.
Yeah.
So this would be a traditional storage array that most enterprise engineers would recognise, and it occupies 5U.
Yeah.
To tell you just how important it is. What you're looking at here is the new fun toy in your data center, which is the water-cooled racks. These are all like fully water pumped, and they're actually chilled, and they're running chilled air around the data center.
Yeah, so the theory is here that well, in fact, we know it's true. We can put at least 30 kilowatts of rack through these, and probably a lot more than that. But the air temperature going in on one side gets blown back out at exactly the same temperature, even with 30 kilowatts of rack inside. So that's for the very dense compute for the whole data center, not just for JASMIN.
Now, this is compute servers here, not storage servers.
Right. Yeah, exactly. Storage servers we wouldn't need this for, and that's why it's in the other rack.
That's the advantage of hard disk drives, is they actually don't generate that much heat compared to a compute server like this. So the storage here is that when they run compute jobs, they're running scientific research. And so when these units are fired up, the CPUs are running at maximum. They're not idling along at 10%, they're actually burning at like 95 to 100% CPU. This is actually sort of like 40 racks long, 35 racks long, of water-cooled servers in here, which is quite extraordinary.
Yeah.
This is all just new, isn't it?
Yeah, this is brand new this last financial year. So, yep.
So there you go. Let's take a step outside and wrap this up. All right, so we've just done a tour around the data center. You've seen some stuff around the network. What's normally the closing pitch? Because you do tours around this place all the time. How do you close this out?
Sure. Well, we usually talk about ease of management and stuff about capital versus recurrent. So JASMIN is very capital intensive, but because we have a small number of people, we have a small recurrent. So that's CapEx and OpEx problems. And that's very unusual for a project of this size. So we have other infrastructures which are have completely different hardware and network setups, which are to some extent are doing very similar things, but they have different CapEx, OpEx models.
Yes.
And so that drives you towards different kinds of hardware. But JASMIN has a very unique data requirements, being a data analysis platform rather than a compute platform.
Yeah.
We're sucking in petabytes of data and turning those around really quickly, whereas other infrastructures are sucking in gigabytes of data and doing some churning around on the compute for those.
So just to think about that, what John's actually saying is he actually has a team of less than 8 people, I think.
That's me and 2 others.
Yeah, right. So 3 people run that entire infrastructure day to day, year in, year out. The only time that other people get involved is at the deployment, so when it's actually purchased and installed. So all the work is actually packed into one single thing, and the day-to-day is actually just done by 3 people. So if you had to build a data center with all that infrastructure you just saw, all that storage, all those computes, and you spend a lot of time doing automation to try and drive all of that, right? You bring in people for projects to help with some parts of that, but the day-to-day stuff is a lot of it's just automated.
Yep. Yeah, that's right. Yeah, I mean that's why the storage choices that we talk about on the tour, they're all ease of management. So they have to just sit there and do their thing. They have to do alerting. And in fact, one of the other things that we did was we worked with a vendor so that a lot of the RMA processes, there are 6,000-8,000 disk drives in that infrastructure that you've just seen.
You're going to be losing at least one a day.
Well, it's not one a day, but it's like I think the average is about one every week to 2 weeks, something like that. But the actual process of doing an RMA, if you're doing it in a small thing, you might lose a drive once every 6 months. It's not a problem to ring up the logistics, log the messages with the vendor, get an RMA, exchange the part, get an engineer out. But if you're doing this every week, it's a substantial period of time. And so we actually we work with the vendors to create a process that where the only time we actually had to do things was just changing a disk drive. So they'll do all of that work for us, and then we just come in and we change the disk drive. We have a bunch of on-site spares for a lot of this cache, And so that means, and then they come in once a month or once every 2 months, pick up the bad ones and drop the new ones off.
Cool.
So.
Well, I think we're going to wrap this up here. It's probably a bit of a longer video than normal, but that's okay because I think there's some really cool stuff going on here. Hopefully this has given you some ideas. Thanks very much to John from the STFC for coming on.
Okay, no problem. Yeah, thanks, Greg.
And if you like this and you want to see more of it, head on over to packetpushers.net where we have a lot of podcasts where we talk about exactly the same things. More like this, nerdy, kind of strange, and on topic. Thanks for listening.